Ever wonder what's really going on with a speeding car? Or, what gives a stretched rubber band that snap? Well, it all boils down to the physics of motion. And today, we're going to break down two of the biggest players in that game, the energy of movement itself and the energy that's just stored up, waiting to burst out. So, let's dive right in. Okay, here's our game plan. First, we'll tackle what kinetic energy actually is. Then, we'll look at the link between work and energy. After that, we'll get a handle on potential energy, and we'll wrap it all up by seeing how this works with a spring. All right, first up, what exactly is kinetic energy? In the simplest terms, if it's moving, it has kinetic energy. It's really that straightforward. We're talking about a thrown baseball, a river flowing, even the wind. It's the energy an object has just because it's in motion. Now, if we want to get a bit more technical, kinetic energy is basically a type of energy storage that's all about speed. The relationship here is super simple. The faster something's going, the more kinetic energy it's got. If it slows down, that energy goes down. So, the bottom line, speed is everything when it comes to kinetic energy.
So, that begs the question, right? How do you actually change an object's speed, and with it, its kinetic energy? Well, that leads us straight to our next big idea, the connection between work and energy. This is where force and motion really team up to make things happen.
Okay, this right here is the heart of it. It's called the work kinetic energy theorem, and it's a fundamental rule of the game. So what is work? In physics, it just means applying a force that causes something to move. And what this theorem tells us is that the amount of work you put in is exactly equal to the change in kinetic energy you get out. So if you push a box to get it moving faster, the work you just did directly increased its kinetic energy. It's a one-to-one deal. All right, talk is cheap. Let's put this into practice with a real example. Imagine this. We've got a 6-kilogram block just sitting there, at rest. We start pulling it with a steady force of 12 newtons. We keep pulling it for 3 meters. The big question is, how fast is that block going to be moving at the end? This is a perfect way to test out our new theorem. Okay, let's break this down. First things first, we got to calculate the work we did. Super simple. Work is just the force times the distance. So that's 12 newtons times 3 meters, which gives us 36 joules. And joules, by the way, are just the units we use for energy and work. Now for step 2, we bring in our theorem. That 36 joules of work we just calculated, that has to be equal to the change in the block's kinetic energy. So for the final step, we just plug that 36 joules into the kinetic energy formula and solve for the final speed. And when you run the numbers, you get 3.5 meters per second. There it is. So by putting in 36 joules of work, we gave that block enough kinetic energy to get it up to that speed. You can really see how force, distance, and energy are all tied together. It just works. So we've nailed down the energy of motion. But what about the other side of the coin? Let's switch gears and talk about potential energy. I love this idea. If kinetic energy is the energy of doing something, potential energy is the energy of about to do something. It's all about stored energy, just waiting for its moment, based entirely on where an object is. This really puts it into perspective, doesn't it? Kinetic energy is the energy of motion. Potential energy is the energy of position. Think about a car speeding down the highway. That's kinetic energy. Now think about that same car parked at the top of a very steep hill. That's potential energy. One is happening now. The other is what could happen. Now, potential energy isn't just one thing. It comes in a couple of common flavors. You've got gravitational potential energy. That's the energy an object has because it's up high and gravity wants to pull it down. But the one we're really going to focus on is elastic potential energy. That's the energy you store in something when you stretch it or squash it, like a rubber band or, you guessed it, a spring. And that leads us perfectly into our final section, where we're going to see all of this in action with a spring. A simple spring attached to a block is seriously one of the best ways to see potential and kinetic energy do their little dance, converting back and forth. Okay, take a look at what's happening here. See the hand pushing the block? That push is an external force doing work on the system. Now, look over at the bar graph. As the hand pushes, the total energy of the system goes up, and you can see that all of that new energy is being stored as potential energy. We've basically just charged up the spring. And this is where the magic happens. The hand lets go, and now the system is isolated. Watch those bar graphs. As the spring uncoils and pushes the block, that orange potential energy bar goes down, and at the same time, the blue kinetic energy bar goes up. The energy is literally transforming from potential to kinetic right before our eyes. But, and this is the crucial part, look at the total energy. It doesn't change one bit. It's constant. The energy isn't going anywhere. It's just changing its costume.
And you know there's got to be a formula for this, right? This equation here tells us exactly how much potential energy is stored in that spring. Let's look at the pieces. That K is what we call the spring constant. Just think of it as a measure of how stiff the spring is. A really beefy spring from a car would have a huge K value. That X is just the distance you've squished or stretched it. So how stiff the spring is and how far you deform it, that's what determines how much energy you're packing into it.
So what's the big takeaway from all this? If there's one thing to tattoo on your brain, it's this. Energy is not created or destroyed. It just changes form. What we saw with that spring is a perfect example of the law of conservation of energy. In a nice, clean system, energy just cycles back and forth between potential and kinetic over and over again. It never, ever disappears.
But that leaves us with a little bit of a puzzle, doesn't it? Everything we just talked about, that was in a perfect, frictionless world. But out here, in the real world, things slow down. A block sliding across the floor eventually stops. So if energy is always conserved, where does it go? What happens to all that kinetic energy when friction brings things to a halt? Something for you to chew on. Thanks for sticking with me on this one.